In order to see that T star has, of course, V minus L leaves, all you have to do is draw a bounding edge like I did here. Bounding rectangle about the skew diagram whose lower and upper corners are coincident with the first dot, drawn, and so on. Then this rectangle has L dots, obviously, by our construction, and L star dots. And if you add up these two from my construction, you get diagonals going down this way. And the sum of these diagonals, the diagonals are the same as the number of edges. And we know that there are V minus 1 edges in any order tree with 3 vertices. And from that, you easily determine that the number of leaves in the map is V minus 7. The other simple question that one might ask here is there a labeling of T and T star with bimapping so that the vertex I in the original tree is going to be a leaf if and only if I is also a non-leaf in T star. For that, I would simply show you the map, the possibility of doing these very quickly. You just label these things in order in an increasing fashion. You use these diagonals, you pass into the image, and now you label the vertices up there in decreasing order, and you notice that 1, 5, and 2 are the non-leaves here, and they turned out to be leaves up there and so on. So a little bit of, if I have time to talk about a human proof, we want to extend the generating function C, where here x keeps track of, I mentioned that. So the x is going to keep track of the number of leaves, and the y is going to keep track of the number of vertices. And this is just the standard extension of what we saw before. And we can also obtain a nice recurrence relation or a functional equation that is satisfied by C by constructing our trees step by step in this fashion. What we are doing is bottom up. So you're starting with a tree here. The tree could be trivial or non-trivial, and you're adding the root up here. It's a bottom up construction. Okay? So if you do that, it's very easy to see that our C satisfies this nice functional relation, and we can get rid of the plus sign and obtain this. And in fact, this particular expression has so many information embedded in it. One of them is Lou Shapiro's observation. This is just a count one kind of exercise. This is what you wanted to see. And if you put into the functional equation, you can easily obtain that. But it has more than this. I just wanted to show you this very quickly. Recently, q-Analogues of Catalan numbers have appeared in many mathematically deep works. If you want to see, just read a paper by Hyman, and it's available from here. But what I'm trying to do here is use elementary tree enumeration problems to introduce a parameter that might provide a q-analogy of Catalan numbers using ordered trees. If you assume ordered trees are just elementary facts. And here, if each leaf in an ordered tree has a unique path, as we know. So the path length of a leaf is the number of edges on its path, and the total path length in this case is the sum of these paths. So there is a repetition in my counting. Okay? So, and if you add that third indeterminate q here, that keeps track of the total path length, that is repetition, some of the edges are counted twice and so on, then we might improve our previous functional relation a little bit and get some results. Those of you who are confused about my thing here, if you take this ordered tree, this particular ordered tree contributes x to the 4q to the 7y to the 7 to cq of y length. X is the number of leaves, that's total path length, the number of vertices, and so on. Okay? So with this, each choice to be made between an existing tree counted by C or a new leaf is going to be counted by x, q, y. And then the ones that are non-leaf are going to contribute x, q, y again. And if a tree with L leaves is chosen instead, then the path length of each of its leaves is increased by 1. Hence, the total path length is increased by L. And I can make a simple adjustment of x to xq in my formula for cqy and obtain this nice expression when you add one more indeterminate in there. And Dominic introduced the cube common symbols here before, so I'm going to repeat that, the cube symbol in the morning, so I'm going to be using that. I want to state a generating function CQXY, which is given by this expression here. Now, Doron might look at me and say that, what in the world are you doing in here? What you going to get out of this? So, well, the answer to that, well, there is an outline of proof. I'm going to skip through that very quickly. The solution, in fact, is soluble. By that I mean it's possible for us to write a small piece of method program and get something out of it. For example, the number of ordered trees consisting of 12 vertices, exactly 8 n nodes, and total path length of 15 is 540 and so on. So what that means is the previous generating function can effectively be used to get some information with a given statistics and so on. On the other hand, you can also apply the theorem to some big problems that a lot of people use big machinery and so on. Most of you are familiar with polyomino and parallelogram polyominoes and so on. So I'll just put one example up here. So counting these kinds of structures by the number of cells, by the perimeter and so on is the kind of usual problem that most of you are familiar with. What I'm trying to say here is you really don't need a whole lot of big loaded machinery in here. All you need is the Skew diagrams, just translate into dots, translate these into an ordered tree. And now notice that if you compare this parallelogram polyomino to that ordered tree, the number of vertices is half the perimeter, and the total path length, if you count 2 here, 1, 2, 3, 4 in here, 2 there, if you add them up, it's the same as the number of cells in your parallelogram polyomino, and therefore you get a nice result for counting parallelogram polyominoes, for example, by area, and I call it semi-perimeter because it just gives you only half and so on. There are a whole other things that you can do with that generating function, but because of...
if you know that similar, so that's a new proof of something you know his students did?
Well, this is just another proof of his result. We're just using order chains. So these are some relevant references, and I wanted to say happy birthday. Questions from a comment?
Yes. How do you get a T-shirt like that?
A T-shirt like that, we talked to Zeilberger, and he might need
My son actually made those things. And I believe what it calls from Ghostbreakers? Ghostbusters.
Other questions or comments?
Aaron and Hal and I had a paper with something really similar with a pattern avoidance. I forgot the details. Do you know of any relation to...
There is a little bit of relation. In fact, a colleague of mine, Dr. Jani, who is sitting in the back, they extended that paper, but in their case, what was the method used? You didn't look at order trees by, it was order trees by level number, right?
Level by level.
Yeah. All right.